Hello and welcome to Lesson 10. This is part 4, and our next topic is extended period simulation. So we're now taking our models from a single steady state thing into a series of steady simulations, and that can be used to approximate the behavior of tanks filling and draining, pump performance moving up and down the pump curve, and ultimately, it's necessary for the water quality component if that's something that's important in a particular analysis. The EPA tank models we've discussed earlier in the course, and storage concepts we've discussed. But the next topic is the multiple period simulation. So multiple period simulation is explained in the following fashion. EPANET and similar programs find steady flow solutions. The extended period simulation produces a sequence of steady states with approximations for tanks filling and draining. Pressures can be different at the beginning and end of a time interval, hence pump operating points can move along a pump curve. It cannot capture pressure transients that occur for pumps starting and stopping or valves being closed rapidly. That's beyond the capability of EPANET as it's currently implemented. Extended period simulation is used for modeling pressure in systems during changing demand, usually at an hourly time scale, storage tank operations and sizing, and water quality simulation. EPANET can approximate water quality from multiple sources, which has uses in determining water age in the system, detection of system intrusions, and severity of contamination from such an intrusion, or an impact assessment. Also with some using the multi-species extension, you can actually determine mixing of different source waters directly, and you can actually solution stack it with the basic EPANET and achieve the same information. So how's it implemented? Well, in EPANET, we assign demand to a node. We can also create something called a demand pattern. Think of it similar to a pump curve, but instead of dealing with flow and head, it has time on one axis, and it has multipliers that are applied to that base demand at those different times. So if the multiplier is all 1, then the demand doesn't change, but in the case where for a particular time interval the multiplier is set at 2, then the demand at that node is twice as big as its base demand. Then we have to set simulation times, and then the program will follow the pattern. So the program will start at hour 1 using whatever that demand pattern is. Maybe the multiplier is 1. At hour 2, maybe the multiplier is 1.2. Hour 12, maybe it's 3, and then we get back to hour 24 and it's back to 1. So we're going to build a single period model, and then we're going to use it to adapt to multiple period. The layout's on the server, and in fact I'm just going to directly go to the server and grab the necessary model information. This one's a little more elaborate, and it would take too long to literally build the model live on the video. So the class server is log in as guest. I think that's all I need. Yay. Alright, so we go to lesson 10, and we, I believe, are at example 8. The easiest way to find it is I'll just go ahead and do the download. Okay, download linked file as. We will put it into the Playhouse. Download link file as, and we will put it into the Playhouse. Now we have to get our implementation of EPANET up and running. Level 8 BMP. Okay, this is what I'm after. So this is the network that we're going to examine. Let's see if I can get, there we go. That part is what we had already, with the exception of this new tank here at node 8. There's a new loop added down here, and then there's another pump and reservoir over here, and then there's this branched portion of the network down here in this corner. Okay, let me see if I can actually get the... And so here is the network now actually built. And if we were to load in the backdrop, they're not going to be identical. Let's see, add a vertex. I'm cheating because it looked like whenever I built the network, I didn't include that corner node. All right, let's see what we can do in terms of getting everything to fit. There we go. So there's most of our, pretty much that system. Let's go here and check options and times. And this one is currently set to run for 24 hours. So for a multiple period simulation, we have to change the duration of the simulation. And we have a demand pattern, which is 1 everywhere. So here the multiplier is 1 at the first hour, second hour, third hour, fourth hour, and so on. And then there's a diagram here to show that. Okay, so if I run it, I'm not sure if this will run or generate an error. Oh, it did run successfully. So if we look at hour 1, there's the simulation. I'll go ahead and pull up some options and flow. So everything's set. We'll do pressure and flow. There we go. And over here is like a tool to advance the snapshots of the simulation. So this is day 1 at at 12 a.m. midday. Excuse me, midnight, 1 in the morning, 2 in the morning, 3 in the morning, 4 in the morning. And you'll notice the numbers are changing even though the demands are constant. And what's happening is these tanks are all filling based on their starting condition. So the importance of this particular simulation is that we have a base from which to adjust our patterns. Let me go back to times. And let's go ahead and put the total duration back to 0. I believe that's an admissible value. If I run it again, I have a successful run, and there's single period, nothing of interest here. So from this network, we will now go ahead and proceed to add features. So we'd sketch the layout on the paper, done, identify diameters, done, 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 and we have the base model built. And now we want to go ahead and insert from some additional information. So here we have the pump curve, another pump curve representing the pump. We have at-grade storage, elevation storage relation. So we'll go take a look at that back in EPANET in a second. All the input information shown here. Some of the pipes are connected to fixed grade nodes. So those represent the various reservoirs and or tanks in the system. We have the base demand. Now this is the important part. So the base demand is what was done in that single period simulation. Then we're going to use demand multiplier. So here's an example of a chart that has a generic demand ratio, percent of average day for the maximum day of the year or a typical winter day for this community. It's taken out of one of the readings. And the max day for year would be probably what we would be interested in for a design or operational design. And so it starts pretty much at the base demand, ramps up until we have a first peak around 210% or a multiplier of 2.1 at 9 in the morning. It then drops down at noontime we have a peak right there at 9 in the morning. We have a valley right there a little bit after noon. Then we have the evening peak at about 9 at night, and then it repeats it. And so our multiplier curve looks like that. And here it is in tabular form. So for hour 1, the multiplier is 1. It goes down a little bit. And we're just taking values off of that curve, converting percents into multipliers. So 300% is a multiplier of 3, 100% is a multiplier of 1. And then we're going to associate it with clock time. The first clock time default in EPANET is midnight of the particular day, or and then it proceeds that way until it gets to hour 23 and then repeats itself. So we're going to build the network layout, which is done, and we're going to want to add the pump curves and the storage curves and demand patterns. So this is what we have in EPANET, and we will go ahead and look at it carefully. So storage curve number 1, excuse me, that's pump curve. Pump curve number 1 is this one in gallons per minute, and that associated with pump 1, which I imagine is this guy. Pump curve number 2 is associated with this pump. And curve number 3 is the storage curve for the tanks that are assumed to have identical storage behavior. So this column of height represents depth above the tank bottom. And so if we're at 0, there's no storage. And if we get (50 feet of depth, so these are pretty tall tanks. These would be like our Stad pipes earlier in the course. If we have 50 feet of depth, the storage volume is 350,000 cubic feet. If you're familiar with the size of an acre is 43,560 feet. So this is basically 10 feet of water distributed over 1 acre of volume. So that's a substantial tank. All right, so that's our base case. And the next thing we need to do is add a new pattern. So we could go that to the editor. We could rename, produce a new pattern. choose the right button. There we go. Okay, so this is the variable demand. And we are going to make it fit that pattern. Let's see if I can get this big enough so I can have both things open at once. Okay, I can practically read that. So here we go. 1.0 for the first one, 0.9, 0.9, 1.0, 1.15, 1.25, 1.5, 1.75, 2, 2, 2.10, 2 again, 1.7, 1.6, 1.45, 1.45, 1.65, 1.90, 2.3, 2.5, 2.8, 3, 2.75, 2.8, 1.25. So there's my demand pattern for my maximum day, and it also keeps track of the running average, and so this is basically a daily multiplier of about 1.8 times the average day. So this would represent a pretty large community if you remember lesson number 8, where there were average multipliers and then we had hourly multipliers. Curves like this appear in the literature, and there's not many available, and they're generally would be tabulated for larger municipalities, or perhaps even certain states would have a typical design curve that one could use. Alternatively, you would have to make flow measurements or assess the behavior of nearby functional systems for which data are available. Okay, so the pattern's entered. So now we need to tell all the nodes to use our new pattern. And so the easiest way to do that is with a group editor. Edit, group edit. I want the demand pattern. I want to choose a 2, press OK, and I'm now ready to run my simulation, which currently isn't very interesting because we need to turn the times back to 24. So there's everything for that. Now if we run it, good, this is what I was hoping, messages. So this thing worked fine until 19 hours. And then at 19 hours, it starts to experience negative pressure. Let's go ahead and just walk through the thing 1 hour at a time, and then we'll see what happens at 19. So everything's happy. Negative pressures will become very blue. 14, 15, 16, 17, 18, here, here, and here, our pressures are getting alarmingly low. They're below the Texas minimum. And our first negative pressure right there. So we know that when we're at the higher parts of the demand period that we can't satisfy the pressure requirements. So our options, we could consider boosting more water with the pumps, or we look at what's happening during our demand period. Essentially what's happening is our tanks are draining. Watch the 6 psi in the tanks, 4. So if the tanks had a little bit more storage in them, it might be possible to get this system to function. So again, that's why these are used as a design tool. We go to our curves. We know that curve number 3 is a storage tank, and let's just have our tank somehow magically contain 450,000 units. We're still having problems, so the tanks actually have to be taller. I'll add 10 feet to the tank. I don't know, a 60-foot tall tank is going to be a lot. And following my pattern, it will be 400,000 cubic feet. These are huge tanks. And now it's still not obeying me. What have I done incorrect? There, after a bit of fuzzing, we now have the model run was successful, and we can step through and watch the behavior of the system as time evolves. Pressures here are getting a little bit on the low side. We might want to choose some color other than yellow, one that we can actually see. I'm going to pick a light magenta. Okay, so if our pressure is in magenta, we're getting close to too low, and if it's red, we're too low. So at 19 hours, our pressure is too low, but it's positive. At 20, 21, and 22. So our options here, we could put booster pumps down here, or we could conceivably put another tank in. For grins, let's just throw in another tank. Right there. We'll connect it. We want to take the same properties. Let's see what my node elevation is right here. I'll just use an identical tank. So those are 220, 30, 0, 50, 50. 220, 50, and the volume curve is curve 3. We run it now, and let's go look at our time. Very nice pressures throughout the system, and we can even let it animate. So we did have a 20 at one point here. So we could consider moving this tank to junction 15. Let's run that. Run is successful. Keep an eye on that one. We get low here, so the probably need some sort of booster system in this region. Anyway, that's how you would use a tool like this to help you do network design and come up with solutions to pressure issues in different parts of the system. So I'm going to delete the tank. Stop this animation, it's bugging me. Another option would be we could put a pump here. To insert a pump, it's easiest just to see, that's junction 13, junction 19. Insert a pump, and we will give it the properties of one of these pumps. So let's let it take pump curve 2. All right, so using pump curve 2, so we insert a pump right there. Let's see what we get when we run the animation. Pretty much no pressure problems on the low side anywhere in the system. In fact, we have too much pressure here. Let's see what happens with pump curve 1. Also way too much head. So when we go to our curves, we don't need near that much head, probably half of it. Let's create a 0, 10, 20. Let's create a fourth pump curve, 0, 10, 20, and 50, 40, 25. Pump curve number 4. Run it. That's better. I think our pressures are a reasonable range. And you now can see how booster pumps are inserted into a network to satisfy. We've got a little bit low down there, so we probably just need to get our pump to be a little bit more say it's something like that. Run it again. Keeping our eye right there. Still need more of a pump curve. I think we got it. We also have an option of doing a time series. We'll do pressure, and we want to choose a node. And we now can look at the pressure at the node, and it does have a low spot at hour 20, a little bit below 35 psi, so we're pretty close on our booster pump. And then we would go ahead and search manufacturer pump curves to see if we could get something close, or alternatively use manufacturer pump curves to prepare the model. So that completes this example. And let's return to the presentation. Okay, so here's the same example done statically. Added the extra 10 feet variable demand, and here's the first few pages of a full output report. For multiple period simulations, the output report reports output for every stress period. So node results at hour 1, hour 2, and so forth. Here they are at 6, 7, and so forth. So we've actually just done this example. 8 and 9, we combined them. So the next topic is going to be water quality, and that will be taken up in a subsequent video. So this concludes Lesson 10, Part 4. Thanks for your attention.